Thank you so much for the invitation to come back to France and give a talk. And tomorrow I'll do a little demonstration, shoeing demonstration. So it's been a long time since I've been back here to France. So thank you very much for the invitation from Dene, my good friend from a long time ago. I think that Dene's probably been a professor or a teacher for a lot of the farriers here. So I've always thought of Dene as my French farrier hero. So thank you for the invitation. I thought today we would talk a little bit about one of my favorite things is the horse's hoof and the difference between the normal hoof function, the upright type foot, and the underslung type foot. So I want to first review some of the characteristics of the healthy normal hoof. It's all about blood supply, and if we can maintain good arterial blood supply, I think we can generate a good quality horn and a good amount of horn that grows. One of our most important features on healthy feet is the sole, is to have a nice thick sole. So you'll hear me talking about vertical depth a lot in this slide. And I refer to vertical depth as the distance that the coffin bone is from the ground and the thickness of the concave sole gives us good vertical depth. And vertical depth in feet gives us a big buffer for any of the inconsistencies that we see in the adaptation or the shape changes in the coffin bone and the bottom of the foot. So as I said, when we trim and manage our feet correctly, we have weight more proportionately distributed, and so we can have good arterial blood flow. This photo is a nice photo showing the, let's see where we are here. You see that? There we go. Kind of seeing the really robust coronary papilla here in this particular breed. This is a Rocky Mountain breed with a thick epidermis, thick skin, and thick horn as well. And it's due to those nicely perfused coronary papilla there. And underneath there, this would be the dermal lamella here. On the other slide, we're showing a good dermal sole, and obviously the sensitive frog in this cuneal region here, and a little bit of the mid-dorsal notch in the coffin bone. That's quite normal for certain breeds. So again, I'm just referring to making sure that we have good arterial blood perfusion so that we can grow some good horn back. When we look at the ideal hoof from the skeletal structure, we like to have the center of articulation, which is different than the center of rotation, and a lot of times is different than the center of pressure. So those are some different terms. But from this view, if we can visualize the center of articulation of the center of articulation of the coffin joint is what I try to visualize, and this is the point that we like to have things balanced around. I will give this Davy Duckett credit for this, for originating this thought pattern of a way to evaluate and balance feet by balancing the coffin bone, or more particular, the coffin joint. Also, you can see in this picture a fairly robust digital cushion on this side, the ungular cartilages, So we see a nice robust ungular cartilage here, and I just wanted to make sure that you saw that the end of the palmar process of the coffin bone ends before or ahead of the point of the heel. And so the back part of the heel inside the hoof capsule is cartilaginous, and it's part of the axial projections of the ungular cartilages that have been nicely shown to us by Dr. Up in Michigan, Dr. Rob, what's his name? Digital cushion guy up in University of Michigan. Yes, thank you. And so it was nicely described there, and I want you just to see that on a normal foot, we should have some distance between in the buttress of the heel, between the end of the heel and the coffin bone. Okay. Also, I want you to notice the perforations in the ungular cartilages, and these are baffling perforations that led venous blood through the hoof at a specific rate. So it's important that these ungular cartilages are healthy, and they are a part of the blood circulation of the foot. Remember now that the blood in the hoof is not only serves to be a nutrition source, but also the blood in the hoof is a mechanical structure and helps to form up the hydrostatic cushioning effect of the foot. And the baffling system of the ungular cartilages is an important aspect of that. And these are what I'm referring to as far as the baffles of the ungular cartilages there. Those let venous blood, and only venous blood, through from axial to abaxial as they come out and drain the rest of the hoof. We'd like to see on a nice foot a good healthy frog. So this is a picture that I had on my computer. I wished I had a little nicer hoof, but this is a nice frog, and so I'm just talking about the frog. So we'd like to see a nice massive frog, a frog that takes up at least 1/3 of the surface area of the foot. We'd like to see it well connected here in the central sulcus and have nice deep collateral grooves on either side. And we also, as far as trimming frogs, it's important that we don't over trim frogs, but we substantiate and help frogs to grow in some vertical depth as well. If we look at the normal side view of the loading patterns of the hoof, I've identified the zone that I like to use from the solar view right here, and this is the central palmar zone, and the lines of the central palmar zone are designated by the Duckett's dot, which is 10 millimeters back from the point of the frog. Back to this point here we call the frog bridge, or this is the point directly under the center of articulation. So here's the center of articulation of that foot, and as we come straight down, we can see that it doesn't divide the foot into 50% in front and 50% behind most of the time. So when we add the additional line made by the Duckett's dot, we have this pink zone here called the central palmar zone. And that's the zone that I like to have centralized in the foot, the same amount of foot ahead of and behind in most front feet anyway. The blue arrows are referring to what we'll kind of refer to as force vectors. So the force vector, the force that's coming down the cannon bone is diverted at the skeleton into the digit. And this fetlock joint is one of the main characteristics of good, healthy, moving horses. And so as the weight comes down the cannon bone, it's deflected into force vectors. There's a horizontal force vector and there's a vertical force vector. So I just want you to understand that the one force is down and one force is forward. And this is referred to as the horizontal and vertical force vectors. On normal feet that are well balanced, this horizontal and vertical force vectors are in equilibrium. And as we get farther and farther out of balance, either on the more upright foot or a more underslung foot, these force vectors change, which affect the loading of the hoof and other elements of the hoof that we'll talk about. So I wanted to talk to you a little bit about how the hoof wall bears weight. This is a little schematic that I've drawn up, just showing how the coffin bone, when it loads, is stretching the laminar bed, the interdigitation of the dermal and epidermal lamina, which then transfers that load to the hoof wall, which then loads the ground on a compressive force. The ground reaction force is an equal and opposing force pushing back up on the foot at all times. And so that is not the same on the inside of the foot as the outside of the foot, meaning the inside wall and the outside wall don't take the exact amount of force. So the inner part of the hoof wall is taking more force than the outer part of the hoof wall, similar to how a medial part of the leg takes more force and load than the lateral part of the leg. One in the static loading, and two in the dynamic loading of the fetlock as the fetlock rotates axially under full load, which loads the inside of the foot more greater proportion than the lateral side of the foot. So this is kind of normal foot anatomy, normal foot biomechanics. I bring this photo up just because later on when I'll go on about a shoeing method for underslung feet, I want you to refer back to and remember how the normal loading of the hoof wall takes place if we're going to control that or change that by using shoes. So this is again, a normal foot showing the digital cushion. Now this is a thoroughbred foot. It's a fairly healthy thoroughbred foot. And I want you to notice the digital cushion. This is the pars torica, the top part of the digital cushion. It's a very important part of the horse's foot. It's a very detailed and highly specialized structure in the hoof. It is not generally made up of much adipose or fat tissues. It has a combination of myxoid tissue, which is tissue that has the ability to change into other things. It has a lot of chondropulvinar ligaments. There is islands of digital cushion islands of fibrocartilage in the digital cushion. And there's a network of series of ligaments that help to support it. So in a healthy foot, this digital cushion helps to support the short pastern under load. If we see the loaded version of the foot on the right, we can see, we can see that the digital cushion is loaded by the flexor tuberosity of the short pastern. So this is the short pastern bone here. And this is the articulation of it in the distal interphalangeal joint. This is the end of the most proximal aspect of the bone, and this is the flexor tuberosity as it's pushing down and loading onto the digital cushion, and more importantly, the frog stay that separates the cuneal part of the digital cushion. So again, the digital cushion is just not a fat pad. It is significantly different in the horse than other species. In the horse, they have a lot more elastin fibers, a lot more collagen fibers, a lot more islands of fibrocartilage, and this myxoid tissue, these myxoid cells, which are like stem cells, and they're able to form up and adapt to the various forces that it has to be put under. So it can be the digital cushion can be overworked or underworked. And when we talk about upright feet versus underslung feet, the digital cushion is completely different. And so I wanted to just make sure you understood a healthy digital cushion is definitely wicked important. I wanted to just show you another version of that so you can see some of the ligaments and some of the organization here. So it's not just a fat pad. Here are the ungular cartilages, robust, healthy ungular cartilages. You can see the perforations, the venous perforations in here that allow the venous plexus blood on the inside of it there. and there to work its way through those baffles, out, back up the leg. The digital cushion here is showing both the cuneal parts and the toric parts. This is the cuneal part of the digital cushion, and this is what we call the pars torica up here. So you can see there's fairly significant ligaments that hold this thing together that give us somewhat of a trampoline effect, and these are chondropulvinar ligaments, and they're wicked important, and they can be developed or they can be hampered depending on the situation. So if the foot is not loaded or if the foot is overloaded, and we're going to get to those two situations. So I've got a little video on the right side here. You can see I've dissected away the digital cushion and its orientation in the hoof. It takes a massive amount of space in the hoof, and again, it's pretty important. If we look on the top picture, we can see the amount of space that it takes up within the hoof capsule when we combine both sections of the digital cushion and the ungular cartilages. So I thought it was fairly interesting to show you this aspect where we have dissected the digital cushion and shown you the amount of space that it takes up actually inside the hoof. So ideal hoof structure, we'll talk about vertical depth. Vertical depth is critical. It is one of the elements that's most commonly missing in lame horses. So when we see a variety of foot lameness, one of the more consistent things we see is a lack of vertical depth. And so our job as farriers, one of our more important jobs, is to help trim feet and manage feet with our timing. The way we do things is to help develop vertical depth, to gain vertical depth, and this is helpful for the horse. When we have a lot of factors that are competing against each other, whether it be genetics or environment, let's say the thoroughbred genetics, or combined with a very wet environment, and some other things like being pregnant most of the time, doesn't help the horn to be able to resist compression, and sometimes we lose vertical depth. And that's when we need to come in as farriers and try to get that back. So this is a drawing from a book from David Roberge. It's a great book called The Foot of the Horse. It was written in 1890. And he refers to vertical depth, and he describes the difference between length and depth. And depth is the distance of the coffin bone is to the ground, and length is the distance from the coffin bone to the edge of the wall. So, for example, we have a long toe. We have we have a lot of length there, and we don't have a lot of depth. So, the solar view of a foot is, this was a good photo. I just wanted to show you how intricate the bars are, where the bars are positioned. But when we're shoeing feet, we're ideally wanting to assess the correct shape of the coffin bone. And as long as that coffin bone is not distorted or remodeled, we'd like to have the white line be the same shape, the hoof wall be the same shape, and concentrically bigger, the horseshoe should be basically the same shape as the coffin bone. So, did you guys understand that? That's pretty basic for you guys. You laughed at anybody in America, they're like, no shit, I didn't know that. So sometimes I just want to make sure that we have some basics. So again, we want the shape of the coffin bone, shape of the white line, shape of the hoof wall, so that we can have the same distance around the coffin bone, or the same length. So the same length of wall from the coffin bone all the way around should be the same. And therefore we can then manage these forces, these tensile forces that cause feet to flare, to dish, or to excessively pull on the lamina to cause wall separations. So on ideal feet, one of the characteristics we like to see is a good tight white line, and have the foot be the same shape as that white line. This is good sole. This is more of a dry-footed horse. This was a horse that was dissected in Las Vegas, Nevada, so he had about 5/8 of an inch, so about 17, 18 millimeters of sole normally on him. So he was very sound, and that's what we like to see, is a lot of sole depth, and we like to see some concavity as well. Now, one of the things I want to refer to it as when we start talking about unhealthy feet is how we can use the epidermal sole, what we call the sole ledge. That is the amount of sole from the white line that fills in the gap to the hoof wall. And we can use this sole ledge. It calluses a lot, and we call it the sole callus. That's what that comes from. But when we have feet with a lack of vertical depth, sometimes we need to use the sole ledge to help bear weight. This is a high-speed film that I took last year with my filming partner, Scott Lampert, and I go out and do a lot of filming on racehorses in particular. This is not a racehorse. It just happens to be a jumper in synthetic. But just to kind of show the hoof mechanism, how important the hoof mechanism is. And you can see the blood, the venous blood, as it's draining the foot, which is aided by a healthy frog and the mechanism of the foot being healthy enough to withstand that. So the temporary distortion patterns of the foot should follow a specific sequence for the capsule to efficiently buffer the vibration and to store and release the kinetic energy generated during the stance phase. So when each structure of the hoof is healthy, the hoof mechanism functions efficiently to dampen vibration and results in optimum arterial blood perfusion, which is also consistent with good venous drainage of the foot. Here's another look at a horse showing the drainage of the blood. Hopefully you can see the venous blood draining, and it's important that we have good venous drainage because arterial blood is coming back behind it. So other elements of a healthy foot, the walls should be straight. There should be no flares so that the lines of compressive force can be dealt with better in a straight line rather than in bent lines like dish toes or flares. Soles should be concave. There should be adequate thickness to protect the underlying chorea and also to recoil after loading. So as the foot loads and the sole flattens, it needs to recoil. If there's not enough strength in the wall, or the thickness of the wall, or the sole is overhydrated, it's not going to rebound effect. So it's important that we have some recoilability, not only in our tendons and ligaments of the suspensory apparatus, but also of the actual foot itself. The ungular cartilages, as we said, should be robust. You should be able to see them and palpate them well above the coronary band, or top of the hoof and the coronary band. You can see we've got fairly good digital cushions on this guy. And yeah, I think you can see them. Good. Again, this is we've seen this picture of the distance between length and depth. So length is the distance between the edge of the bone and the wall, and depth is from the edge of the bone to the ground. Just to make sure that my definitions of length and depth are consistent for you. Now we look at the upright morphology of feet. Now I'm not talking about club feet necessarily. Some people may consider these low grade club feet, grade 1 club feet, but I'm going to just refer to them as upright feet. I'm an instructor at a school, and it's much easier to teach people to learn to shape the different families of shapes of feet than each foot be its own specific shape. So although that's true, as we all know, the upright foot has a consistent characteristic shape. The underslung foot has a consistent characteristic shape. I don't think it's my job to change that shape. My job is to make that shape, make that hoof as healthy as possible. And if I'm going to do that, I have to understand the forces that that foot is now having to deal with. If I'm going to understand that, I first have to understand what normal hoof biomechanics are. So we've just got done talking about normal hoof biomechanics. By the way, does anybody have any questions about what the information that we've just talked about? Everybody good so far? How's the translation? Yeah, it's good. Yeah, I will not try to tell you my stupid jokes because they generally don't translate well. So, okay, good. So, if there are no questions, I'll carry on. The elevated heel and the steep wall angle of the upright foot prevent the foot from impacting the ground in a way that allow the caudal soft tissue structures of the foot to effectively dissipate vibration or dissipate the forces of the heel strike in the loading phase. So there's two phases that I want you to pay particular attention to on the upright foot. One is the landing. Usually, not always, but usually they land very heel hard. And number two, as that, what do we need in the back of the hoof to help deal with that energy, to dissipate that vibration? Well, we need frog engagement is really helpful. But there is no frog engagement much on an upright foot. The frog is recessed up in the foot. It doesn't have much the ability to do its job. So consequently, the foot adapts to that, and it narrows in the heels, and the heels become quite atrophied. The frog becomes atrophied. The frog very commonly is sick and has a central sulcus that is now ruptured through, and a lot of bacteria in there. So that's the first stage of that, is the heel strike. On an upright foot, there are well-developed ungular cartilages and digital cushions compared to the ideal or compared to the underslung foot. So you might ask, well, how come if the digital cushion is designed to respond, and it does, and the digital cushion responds a lot like our skin. And when our skin is challenged, it calluses and gets hard. When the digital cushion is challenged, it creates more ligaments, it creates more, the myxoid tissue reacts and creates a more significant cushion, a cushion that's much more able to dissipate shock, vibration, hold and store and release energy. So the release of the energy is quite important as well. So the second part of the upright foot I'd like for you to pay attention to is the loading phase. So on the loading phase, we don't have the ability for the short pastern bone to completely load the foot. Maybe I should go back and show you and talk about this. So on this picture, you'll notice that the short pastern bone is loading onto the top of the digital cushion, which loads onto the bottom, the cuneal part, or what we'll call the plantar cushion. The plantar cushion then hits the ground. The ground pushes back with an equal and opposing force, and everything is in equilibrium. But when we don't have the frog to contact the ground, then we have some problems. Right? So what happens is the short pastern touches the digital cushion, but the digital cushion touches the frog, but the frog doesn't touch the ground. And there's the problem. So now all of that force is put onto the skeletal and ligamentous anatomy of the digit. This is one reason we see a lot of ring bone and a lot of skeletal arthrosis and a lot of skeletal remodeling of the pastern bones in upright feet. It's not necessarily because of the shock and concussion, but look how this horse is loading at mid-stance. So on this picture here, we can see that this horse is loaded to a maximum. Now I've got a loading cell, and so I have a a gauge to tell me how much force is there. And this is in normal parameters. This is normal loading sequence of a normal upright foot. When that happens, the fetlock doesn't drop. There's not as much motion. And as such, it's not being able to utilize the frog, the digital cushion, and the ground to help support it. Does that make sense? You guys with me? There's nothing for him to sit on. So it's all on the hoof wall and all on the ligaments of the digit, especially of the pastern bones. So as a result, in this stage, we can see that the pastern joint is subluxated. The pastern joint shouldn't be this subluxated in a normal loading pattern. I can take you back and show you a normal foot, normal loading, and you can see how the pastern bones and the pastern joint is not subluxated like that. Okay? So you can see the coffin joint is flexed, but the pastern joint is fairly straight. So the articulation of the pastern joint only occurs at the very end of the loading phase and just prior to heel off. So there's about a 5-degree range of motion of the pastern joint. And when the pastern joint articulates or subluxates before it's ready, then that's when we start having some issues with torn collateral ligaments and a lot of other issues like that end up being, like ring bone looking x-rays. Okay? So this is our upright foot. Notice how when we load this foot, again, the pastern is not down. A couple of other things are happening. Number one, we have a lot of mass of horn here. There's a lot of horn. So as a result, the heels don't open and close as much. It's very stiff back there. So there is some movement, but there's not as much movement as in a normal foot. On an underslung foot, in response, it's too much movement. There's too much movement in the back of an underslung foot. So I wanted to show you what normal is, and then what abnormal is on either side of normal. So on the upright side, the heels are massive, they're high. Yes, they're strong, but, and I say that upright feet are kind of survivors. They're the dirty little feet that always seem to be there for us and don't have a lot of trouble with them. We have a lot more trouble with underslung feet, but nonetheless, they have some issues that we can make them more efficient to function more efficiently if we understand the dynamics. So as we carry along, the weight distribution patterns in upright feet is we have an excessive amount of anterior loading. So the weight is more distributed in the front half of the hoof capsule. That's why the growth patterns are changed. We grow more heel and we grow less toe. But something that a good friend of mine, Dr. Hans Kosselens, kind of opened my eyes to is that it's not always just growth. It's a lot has to do with wear. So you think about heels, how we say, sometimes heels don't grow. Well, when we talk about the underslung foot, if we look at the growth rings, how many times have you looked at growth rings and they're the same, right? They're not divergent. They're the same growth in an underslung foot, but he's not growing any heel. Y'all with me? You guys with me? You know what I'm talking about? So we have an underslung foot that we can never trim any heel, right? Why? Is the heel not growing, or is the heel being worn away? Hello? 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 Bonjour. What do you think? Canada. You think it's worn away? Yeah. Yeah, for sure. And that's something that didn't really click in my mind until later on in my career, is how important wearing is. So the wearing factor is really important. So that's just it. It's not only about growth, has to do with wear as well. So on these upright feet, the growth is, the growth patterns are a bit different. There's diminished blood supply to the dorsal coronary plexus, much like approaching some laminitis horses that have some occlusion of blood in that front part of the foot, just because of the weight there and the extensor process. So the reduced growth rates and increased wear and load in the dorsal hoof wall result in a compensatory heel overgrowth, creating progressively morphological distortions that gets worse over time. And one of the things that I'm concerned about, and I look at a lot in an upright type foot, is how much the coronary band is distorted. You can see on this white foot, I've got a nice white foot here, and you can see the bruising, and it's pretty consistent with upright feet that we see bruising. And we need to know where bruising comes from. Does it originate at the coronary band, or does it originate in the sole? Because we see bruising in the horn tubules of the heels of upright feet, actually within the interstitial horn itself. And so you can see a lot of this occurs up here in the coronary band because of the excessive heel loading when they hit the ground. Now this photo, I'm trying to show you the difference in force vectors. So we have a little bit more of a horizontal force vector and less of a vertical force vector on an upright foot. This results in a dishing of the toe. It results in a jamming of the heels as well. So one of the things I like to do is to look at the coronary band, and if the coronary band is jammed up and humped up, that lets me know that I've got some work to do on my heels. Okay. This is just the loading, just that foot being loaded back and forth. And you can see that there's very little expansion in the heels. There is not a robust frog, and you can see how the frog spine or the frog stay is not well connected and prolapses out when the foot's trying to reach the ground. So the hoof mechanism is not functioning optimally. The height, the angle of the bars are preventing the kinetic chain of support from the ground to the digital cushion. So we don't have a connected chain of energy from the bone to the ground. There's a gap there. And that gap is now filled up with the ligaments of the foot trying to support that under load. So again, you can see on the right-hand side here, there is, can you guys see my pointer? On the right-hand side here, the picture on the right is showing that the pastern joint is subluxated, and what's going on is all of that force is now taken by the ligaments of the digit rather than being aided and helped by the ground. The upright foot interacts with the ground different than the ideal or underslung foot. And one of the things that happens is what I'll call the secondary toe strike. If you can notice this galloping horse, he hits heel first and then his toe slaps down. So, does anybody have any ideas on why deep digital tendon flexor injuries occur as opposed to superficial digital flexor tendon injuries? Does anybody have any comments? All right, let's take this guy. This guy is a trotter. He's landing heel first and slaps the toe down. And there's a lot of energy that's not good energy when he slaps the toe down. Number one, he's decreasing the slide phase. He's not allowing the foot to slide. And what's happening in the slide phase is a lot of energy vibration is being dampened, and it's not able to do that. The other aspect in this excessive, it's a little bit like, now on the opposite end, we go to an underslung foot, a jumping horse. So we have a horse that's jumping over 1.6 meters, and if you've ever looked at the high-speed videos of the horse hitting, their toe generally hits first because they're searching for the ground. Their toe hits first and it slaps down. And this slapping down, right, is a lot like it's hard on the tendon. Can you picture that? Here, I'll show you. So it's like this. Right? The tendon slaps down. Can you picture that? And so maybe that is a contributing factor to why we see more deep flexor tendon injuries in jumping horses and more superficial flexor tendon injuries in galloping horses. Amen? Anybody agree, disagree? Yeah, this sounds logical? Okay, we're going to go with it. That's just my, that's not scientifically proven, that's just my point of view, okay? So, when we hit hard and slap down the toe, it's not good because we decrease the slide phase and a lot of vibration is generated. And the underslung foot, when we come down and hit on the toe first and then slap down, it's not good on the deep digital flexor tendon. So, the digital cushion development, we've talked about it, pretty good in upright feet. It has a lot more elastin, a lot more collagen, and a lot more fibrocartilage in that digital cushion. So we're wondering, why would the digital cushion be healthy when it's not challenged? Well, it is challenged. It's challenged from the bone down, but it's not opposingly challenged from the ground up. And so we find the two areas of the digital cushion, the top part, which is called the pars torica, and the bottom part called the pars cunealis. It sits in where the frog is. That part, they're different, and they have different ratios of fibrocartilage and these chondro ligaments that go in there. So there is a huge difference, and it adapts. So strategies of managing an upright foot. I've stopped in the last 10 years or so, I've stopped trying to make feet symmetrical. I've just understood that most horses have one more upright foot than the other, usually. So I tend to deal with shoeing horses more for the limb rather than trying to make exact perfect match pairs. I did a little study one time on the hoofbeat system. I don't know if everybody knows what the Workman Black or the Workman hoofbeat system is. And I did a little work on that on a upright and underslung foot, so a high-low case, and showed that the rocker, I dealt with those two shoes differently, those 2 feet differently. I did various rockers. I did a different rocker on the upright foot than on the underslung foot, and we were able to, instead of trying to make them the same, we just accommodated each limb, and it seemed like it worked better for the horse. Who was much more comfortable. So I didn't try to match them. I didn't try to take all the heels down off of the underslung foot and chop all the toe off to make them visually look the same. I treated both of them biomechanically different, and that seems to be my mindset nowadays. So if we're going to do that, we do have to manage the heels, but we don't want to trim too much off the heels because they will can very easily make them sore. So one of the things I do is do a digital extension. So you can have Hans Kosselund has a digital extension device. You can use a wedge pad. You can use bar stock. You can use anything to make sure that if you're going to trim his heels, that he can handle that heel trimming. And I will trim heels on an upright foot, mostly depending on the rounding of the coronary band. If the coronary band shows that it's very distorted, generally there's a lot of bruising there. That's my first indication that I want to start to remove the heels. Not anything to do with the hoof pastern axis. So we want to make sure that we don't overdo that. Is everybody clear on what we're doing in this photo? Trying to find out the length of the deep digital flexor tendon that will allow us to drop the heel. So if we can raise his angle of his toe by 12 millimeters, we can remove 12 millimeters off of his heel. So Another way that I like to use, I like synthetic shoes. The two I like is the glue shoe. I like the glue shoe made in Holland. And I like the Epona shoe. Those are two good synthetic shoes. But I usually try to rocker the heels a bit. Sometimes I'll do it in the foot as well, but usually do it in the heels. It helps to have more surface area of the shoe when the heels hit the ground hard first. But the synthetic shoes are good because they tend to dissipate a lot more vibration than a steel or aluminum shoe. So in this situation, I like a synthetic shoe. It allows this underslung or this upright foot, the heels, to move a little bit if we need to move it. And I will facilitate that movement by using a very robust orthotic. So I like to use orthotics with dental impression material to make a frog. The first guy I ever seen did this was Antoine Corona with his frog pads years ago. Came over and had some good frog pads and showed us how to do this. So I just do this with dental impression material. So the combination of synthetic shoes with orthotic support, and what I'm trying to do is to create not a space, but to fill that space so that now we can connect the kinetic chain of energy from P2 to the digital cushion, to the frog, to the ground, and back up again. So now we've filled that gap with an orthotic. It does two things. It helps to dampen vibration, and it helps to maybe keep the heels widened a little bit. So it makes the frog perhaps a little bit more functional. So the combination of synthetic shoes with orthotic support materials creates a synergistic benefit that helps this foot over the long term. So again, I've got two different shoes here. One's an Epona shoe that's nailed on, and one is a glue shoe that's nailed on. I don't like to glue it because it binds up the back of the foot, so I'd rather nail it to keep it open, to encourage widening of the heels. I do like to chamfer it. Just a photo of a cadaver leg I wanted to show you. As the foot hits the ground, when we chamfer the heels, we can increase the surface area for the foot to land on, creating, hopefully, elongating that time of heel strike. Rather it being so harsh where it hits the ground and slaps the toe, it can generate a little more heel strike, or a little bit more slide face. Okay, so I've got two versions of that. Here's the loading of these feet. Let me see if I can get them running. There you go. That's an active slide. Look at that. So to get that upright foot, a normal foot in the middle, and an underslung foot on the right side, just showing them loading. Hopefully you can see how much the foot on the right is expanding, and the angles of the walls are much less steep, and we're tending to now overuse the back of the foot. And on the upright foot, we don't really have a substantial enough horn to support the back of the foot. So the underslung foot, let's talk a little bit about that. There's a combination of factors that set up the conditions for the development of the underslung foot. Genetic contributors are one. So in my country, we've got a lot of thoroughbred horses. Thoroughbred horses have thin skin. They have thin skin, they'll have thin hoof walls as well, because it's all epidermis. The collagenized epidermis of the skin and the keratinized epidermis of the hoof. So these genetic contributors actually have thinner hoof walls and physiologically longer pasterns. So we have a bit longer pastern. That means that puts the forces farther back in the foot, just by nature of the length of the pastern. The environmental factors are important. So the environmental factors of hydration. Sometimes the foot is overhydrated. In my part of the country, feet are wet. If they're outside, they're wet, standing in water until about 11 o'clock every day. And in the summertime, we've got about 2 months where it dries out. But now we're getting back to the wet part of the season where it's just wet and they're standing in water all the time. And this is not good for horses' feet. So they're overhydrated. When we combine that with long pasterns, which overload the heels, combine that with with genetically thinner hoof walls and hoof capsules. We have horn, the back half of the foot that loses the ability to maintain some vertical depth. The bars tend to flow down. From a side view, the coffin bone loses its positive palmar angle and it falls back. We start losing that. And once we can see those things, hopefully we can mitigate them to some degree. So here's a pretty good example of a normal and an underslung foot. Sometimes we have a lot of heel pain and underslung feet, and hopefully you can see by this picture that the heels on this picture are now directly underneath the bone. Yeah, so you can see here that the heels are long. They're actually longer than the heels down here on a nice foot. But you can see now the void that is filled with cartilage down on this foot is now, the horn is overrun now and is now directly onto the palmar process of the coffin bone, which does not make things very comfortable. So we're now starting to have problems with arterial blood flow. We're starting to have problems with now a disorganization and the wrong orientation of the hoof. It's not where it's supposed to be. The center of mass disproportionately migrates caudally. The heels migrate proximally and axially. One of the things that happens in an underslung foot is heels don't expand out anymore. They fold under and the quarters blow out. So the heels fold under and run forward when they're loading and also as they're growing. And so that's one of the reasons that we have to continually trim the heels back on an underslung foot to maintain some length of foot, because the heels are mispositioned. And if we don't keep them short, then they collapse in and start having impingement problems under the sole choreo. So it's just two different views. Here's now the force vectors of an underslung foot. If you can remember, the upright foot had more of a horizontal force vector. The underslung foot, or a long pastern horse, has more of a vertical force vector. Okay, so that's why we're overloading the heels. We're not getting the heels enough time to recuperate, to regrow, to come up for air, so to speak. So they're constantly being strangled and not able to catch up. And so it's up to us to try to use horseshoes to divert weight and load, perhaps to different areas, to give the foot a break. And you can see another thing that's a problem in this is one of the reasons that we have flat feet. So if you've got a flat foot, we pretty much always have a thinner sole, right? Yep. And the thinner sole is because of a lack of blood flow, of arterial blood flow. So you can see here in an underslung foot that's flared, that what happens is the sole, which is normally like this, now the sole is going like this. So the bone normally is like this. Now we've got a lot of length. Bone is pushing down, and the sole migrates up and reshapes. You understand? And so as a result, the circumflex artery, which is here. Excuse me. Oh, you can't hear? Sorry. So where was I at? I'm talking about the migration of the circumflex artery. So we know that the circumflex artery provides the blood supply for the sole chorea. But what happens is when we get too much length, the sole remodels, and the circumflex artery now migrates proximally. Now the blood has to come around the margin of the bone to get to the sole. So this is why we have a lack of vertical depth or lack of thickness in the sole, because of blood supply. So again, it goes back to arterial blood supply. Here's a picture of the length of a normal foot and an underslung foot. This is what I'm talking about. So you can see that the increased length here causes the causes the ground reaction force to push up and remodel the sole. So that's one of the concerns in dealing with underslung feet that I haven't been able to actually have good progress on until lately. So we know that the lack of vertical depth is probably the most consistent factor in foot unsoundness. Okay, so this is just, again, some different views of some underslung feet, trying to show you the migration of the circumflex artery and why. So now we look at this chart, or this drawing again, of normal compressive load of the hoof wall, and how a flared hoof wall that has excessive amount of tension functions. So these gray triangles have the same area. It's called area under the curve. So there's the same area in this triangle as there is in this triangle. It's just that one is stretched out disproportionately. And as feet do that, we lose vertical depth, we lose sole thickness, and then the process begins of problems. So trimming and managing the underslung foot, I've found the best way for me to manage an underslung foot is, don't try to change it into something it's not. Just try to make it as strong as it can be. So I found that turning them out barefoot and trimming them every 2 weeks seems to be the best option for me. But the problem is holding that trim, holding that pasture roll. We have to go back and reapply that chamfer, that pasture roll. So I like to trim the heels to good tissue connection. There's also, I don't know if you guys know about the dimple, Duckett's dimple, the area of the heels, right when the heels start to migrate, start to change. That's the point for me that I like to trim the heels to if I can't find any other landmark. So I hope that makes sense. We like to try to trim them so we got a good connection between the wall, sole, and the bars. We like to reduce the tension on the wall, and I'm going to call this circumferential tension. So it's the circumference of the hoof, and it's tension on the circumference. So I call it circumferential tension. That is the tension on the lamina and on the white line. I do like to use, there is a big sole edge on an underslung foot, so I do like to use the sole edge for loading, barefoot and with shoes. I don't like to overdress the walls and don't like to overdress or overknife the bottom of the foot. So again, as we look at a chamfered foot, and this drawing here, you can see as that foot was going to go into penetrating ground, the ground reaction force changes angle a bit. It changes from straight up to more angled. And you can see how we created some surface area there for the ground to push inward as the foot is stepping down. So that's the idea behind that pasture roll. Using shoes to deal with underslung feet, we can use what we call axial loading. We can redistribute weight to the center axial aspect of the foot. We can use Harpar shoes. We can use dental impression material underneath a wide bar shoe. And what I'm trying to do is to unload a bit the hoof wall, change the where we're loading to the inside and the frog area and the axial portion, and most importantly, loading the commissures with orthotic to have the commissures continue to push and gain more and more vertical depth by giving them an orthotic. Is that, you guys with me? So I like to use orthotic materials in these feet to help give some additional weight bearing and to help restructure the commissures. So I just wanted to show you a couple different force vectors on normal circumference, traditional circumference loading, perimeter loading of the hoof. This is a bit different. This is a spring shoe. And just shows how we're trying to redirect the ground reaction forces. So a flat shoe can decrease the ground reaction force depending on its position although the angle of the wall remains unchanged. So the angle that the foot is taking load on a flat foot is always very similar. We can't change that until we change the section of the shoe. Here's some examples of systems that are trying to reduce the circumferential tension around the foot. A clog, a roller, full roller motion bar shoe, and the spring shoe here. Then we can go to the next step. I became a bit frustrated with these methods. I wasn't able to get complete and total rehabilitation of feet to my desired standard with just using axial loading, nor have I been able to do it with just reducing the tension on the perimeter of the wall. So you guys, Greg Watt actually years ago at the Workman Spring Game showed me this French roller shoe. So him and Hans Kosselans worked on me and got me thinking about this French roller shoe. It makes a lot of sense. I really like it on flat feet. It makes a lot of sense. But again, the French roller shoe, it's not really as dedicated of a rocker as the next shoe that I'm going to show you. You get about this much change. So you're changing the angle now that the hoof wall is bearing from here to there, yeah, like this. This is the French roller, yeah. How many people do this type of shoeing? French rolling. Yeah. Yeah, you don't? Yeah, you do? Yeah. So I think in the States it's called a saucer shoe or a bowl. What do we call it in the States? The saucer shoe. So I've taken that and now put that on steroids. So that's a good idea, but it wasn't giving me the desired results. So what I did was decided to make a shoe like this. I call it a wall buttress shoe. So it is a shoe that's buttressing the hoof wall. It's a buttress, and a buttress is a structure that supports something, right? So like stand up. Now lean back on me, lean on me. Here, I'm going to provide a buttress. There we go. Come on. Very good. Now I'm the buttress. So I call it the wall buttress shoe. Yeah, it's a bit goofy. Yeah, but sometimes I spend a little too much time alone. So the wall buttress shoe does the same thing a French roller does, but with more force. So it changes the angle of the wall even more so. The buttress must be positioned, so it's important that you trim the foot and fit the buttress correctly. It must be positioned so that the wall is loaded less than 90 degrees in order for us to reverse the forces of the wall trying to flare out. Okay, so I'm trying to minimize the toes and the quarters from flaring out, trying to keep feet tight by using this shoe. So the French roller shoe allows me the black line, and the red line, when I change it to the red line, it gives me the angle of the wall buttress shoe. So the angle of the perimeter roll and the wall buttress plates must be less than 90 degrees in order to use the circumferential tension against it. Now what I'm saying is I'm making the hoof wall accountable for its load. So I'm saying we have a hoof wall, it's bent, it's not able to take load. What can we do to make that hoof wall do its job? So this is what this shoe does. It causes the hoof wall to do its job and doesn't allow it to sneak out of it. So this is just a difference of the GRF, the ground reaction forces on the wall. So now the idea is I'm trying to transfer the load from the sole to the wall this way, right? So rather than loading like this, I'm loading more like hanging here like this, if that makes sense. So I'm trying to change the load pattern on the wall. It's not a continuous clip shoe. Make sure it's not this shoe. A lot of people think it's the same thing. This is a completely different shoe. This is an old shoe that we used to use for fractured coffin bones and things like this. We don't use it much nowadays. This shoe, although, the wall buttress shoe, requires that you trim the foot like this. So we can see we've got a nice angle, a nice chamfer there. And rather than trimming the wall traditionally, I just instantly, automatically angle my rasp and just trim the angle into the foot. That's before and after. This is an example of a foot. It's a flat foot. It has a nice sole ledge, and you can see that we have reduced that, and you can see hopefully you can see the angle here that showed in the blue marker in the picture before. So we've just prepped the foot like that. I've got a little block that I made, and we just kind of, the block has an angle. I'll show you tomorrow. I'll do a little demonstration tomorrow, and I'll shoe a horse with this shoe. But that's basically how I do it. It needs to be pretty much a bar shoe. It's hard to do this if it's not a bar shoe because of the distortion of the foot. And it becomes very difficult when we're done making the buttress plates to shape the shoe. So it's kind of a difficult shoe to make. I thought it would be an interesting demonstration for us tomorrow. I hope you like it. So that's making the buttress. Same thing, we just burn it on. And depending on the hoof, depends on how far back the buttresses go. I like to make sure that the buttresses come and wrap around the quarters, and so they don't allow the quarters to blow out. And people say, "Oh, Monsieur Taylor, you have messed up the hoof mechanism," and they say it like that too. And I say, "No, I haven't messed up the hoof mechanism. The hoof mechanism's already messed up because he already has too much motion there. We need to compartmentalize that a bit." And so that's what we try to do, is to make sure that the quarters are maintained. And when we can keep the quarters in, they don't flare out, and we can start to regenerate a little bit in the back half of the foot. This is just a side buttress shoe that I had on a Laminita course, and worked good. So you can see on this picture that we've transferred. The idea is I'm transferring the load from the sole to the wall. So the sole, we virtually have no contact on the sole. It's all on that buttress plate. So if I can do a good job and get my shoe to rest on that and not rest on the sole, I can make some headway, much better headway in gaining vertical depth. And so I just did a measurement, and I took a dental impression material mold on the first day, which I found the sole depth, the concavity was about 3 millimeters. And then this is after one cycle, on just one horse on one cycle. So it's not scientific. It's one horse and one cycle. This picture, that's all. But it's consistent. It works like this. Consistently, I was able to get 9 millimeters of change. So it changed by 6 millimeters in 6 weeks. So we were able to go from 3 millimeters to 9 millimeters of sole depth by making the wall accountable for its load. So I thought that's interesting. I have the highest regard for the French farriers, by the way. Of the farriers that I know in the world, the French farriers are some of the best farriers that I know. And I thought that perhaps you guys wouldn't laugh at me too bad. I'll show you this demonstration tomorrow. Okay? There's some key takeaways for you. Vertical depth is critical. The loss of vertical depth is the most consistent factor in foot unsoundness. Maintaining or restoring adequate vertical depth is essential for successful treatment outcomes. Upright feet need caudal engagement. We have to use sometimes synthetic shoes to help dissipate vibration. Sometimes we need to chamfer the heels, and sometimes we need to use orthotics to engage the back of the foot. Underslung feet require load redistribution. We're going to have to redirect forces from peripheral loading to axial loading and other aspects to try to deal with underslung feet in a manner that keeps them going. Hoof mechanism function. Healthy hoof mechanisms are an important function of the feet. The hoof mechanism doesn't function as efficiently in an upright foot, and in an underslung foot, the hoof mechanism is overused, and the foot is kind of overused, and especially in the caudal part of the foot. So one of the things that I've done is to try to use different shoes to redistribute load, and one of these shoes is the wall buttress shoe, and it works really good to deal with flat feet, underslung type feet to regain vertical depth. So there you go. Thank you for your time.